Welcome you all to the webinar. Today we are going to discuss about the topic UV-Visible Spectroscopy. Let's start with the introduction. So when we see the terms UV spectroscopy, let's understand what is spectroscopy is about. It is a branch of science that deals with the interaction of EMR with matter. What is EMR? It's an electromagnetic radiation. So electromagnetic radiation includes the radiation starting from hello. So coming to the introduction part, if we see here, what is electromagnetic radiation? Electromagnetic radiation actually starts from the high energy waves, that is gamma rays. Then it continues with the X-rays, UV rays, visible, IR, then microwaves and radio frequency waves. So all these kind of radiations comes under EMR. Then what is interaction is about? Interaction is nothing but absorption or emission. Whenever the radiations are absorbed, it is called as absorption spectroscopy. Whenever the radiations are emitted, it is known as emission spectroscopy. Then coming to the matter. What is matter? Matter consists of like ions, atoms or molecules. So when we sum up all these together, whenever the EMR, that is electromagnetic radiation, either it gets absorbed or emitted by an ion, molecule or an atom, the energy, what happens to the sample, it moves from the lower energy to the higher energy. So this is what spectroscopy is about. When we are talking about UV visible spectroscopy, from the EMR, UV visible rays, whatever ultraviolet and visible radiations are there, they get absorbed by molecules. That is the reason why UV spectroscopy is also known as molecular spectroscopy. And because absorption of the molecules are taking place, it is also known as absorption spectroscopy. Coming to the spectroscopy, it is a powerful tool which is available for the study of atomic and molecular structure. So in the EMR, if we see, we have to understand what is the relationship between the wavelength and energy. Because UV radiations, UV visible radiation comes under lesser wavelength. So once you understand what is EMR, you will be able to identify like why these are like coming under high energetic kind of radiations. Okay, so what is EMR? It is a discrete package of energy called as photons, and these photons have an oscillating electric and magnetic field. When you see, when this photon is subjected to energy, what happens here is E is equal to h nu. If you see here, E is energy, h is the Planck's constant, and nu is the frequency. By what you call, by substituting the relationship between the wavelength and frequency, we get E is equal to hc by lambda. So from this equation, we can say that wavelength is inversely proportional to the energy. This is the electromagnetic spectrum, whatever we are observing here. So the rays of interest, that is UV visible region, comes under this region, that is UV. It starts from 200 nanometers and ranges up to 800 nanometers. So 200 to 400 comes under UV region, and above 400 it comes under visible region. And the wavelength here is measured in meters. If you see, this wavelength is increasing here. So whenever the wavelength increases, obviously energy decreases by this equation. So this is how we have to understand how a wavelength affects the energy. So we have seen that in the introduction part, the whatever molecules are there, they undergo transitions. What are those transitions called as? Electronic transitions. So let us see what are these electronic transitions are. If you see this diagram, see, we are having different types of bonding, non-bonding and anti-bonding. If you observe here, three types of terms you are seeing. These are bonding molecular orbitals, non-bonding molecular orbitals and anti-bonding molecular orbitals. What a molecular orbital is, how it is formed is, whenever two atomic orbitals overlap with each other, a molecular orbital is formed. That can be like SS overlap, SP overlap, or PP overlap. So whenever the formation of molecular orbital increases the stability of the molecule, that is known as bonding molecular orbital. Then whenever the formation of molecular orbital decreases the stability of the molecule, it is known as anti-bonding molecular orbital. Coming to non-bonding, it neither increases or decreases the stability of the molecular orbital. They come under non-bonding molecular orbitals, and they also have lone pair of electrons. So by understanding this, we can say that four types of transitions, electronic transitions, are possible. So the first one is sigma to sigma star. So sigma here is a bonding orbital. So the transition takes place from the sigma bonding orbital to sigma star anti-bonding orbital. Generally, this type of transitions, you see it under the saturated compounds where only single bonds are present. For example, if you see here, we have methane. In methane compound, we have CH single bond, right? So the absorption maximum is observed at 125 nanometer for the methane molecule. This transition will take place under very high energy is required, because we have seen, right, whenever the wavelength is small, energy is high. So this, if you check out the maximum absorbance here, 125 nanometer, it is very less, wavelength is very less, because of which the absorption takes place at very high energy level, which is generally not possible, because below 125 nanometers it is not a UV region, and which will generally not see this kind of transitions. And the second kind of transition is N to sigma star transition. In the N to sigma star transition, what happens is, here these also belong to the saturated compounds only. Non-bonding is nothing but which contains lone pair of electrons, the atoms which contains lone pair of electrons like oxygen, nitrogen, sulfur. So these orbitals generally we don't find in a single bond, right, except in alcohols. Remaining all, they are bonded like in a double bond only. So the molecules are very few, because of which this kind of transition, what we observe is also will be lesser compared to the ones. And the wavelength where you observe this kind of transition is 150 to 250 nanometer. Okay, so the next transition is pi to pi star. Pi to pi star, it is the bonding orbital to the anti-bonding orbital. So pi electrons generally is something related to the double and triple bond carbon molecules or organic molecules. So whenever you observe these hydrocarbon molecules, like which contains only carbon and hydrogen, then these kind of transitions are possible. And these kind of transitions occur generally, you can observe it 170 to 205 nanometers, which is absolutely our UV range only, vacuum UV to near UV range. So that is the reason which these kind of transitions are generally possible. And most widely seen transitions are N to pi star transition, that is which undergoes from non-bonding to anti-bonding orbital. Here you will be seeing double, triple bonds as well as heteroatoms with lone pair of electrons are also visible here. So that is what that is the reason why we can say that. And this generally happen at a longer wavelength, that is around 300 nanometers, which falls under the UV region only. So most organic molecules which are available for the identification, that is qualitative or quantitative analysis, generally these undergo these type of transitions. So pi to pi star and N to pi star transitions are the two types of transitions which are most widely seen transitions. That is, the molecules will be undergoing from the ground state to excited state whenever they absorb the UV or visible light. Okay, once we are getting into the topic to UV visible spectroscopy, we should also be familiar with few terms in UV visible spectroscopy. The first one is chromophore. Coming to the chromophore, phore is part. Chrome means color. Any part of the molecule that imparts color is known as chromophore. Generally, whenever any heteroatom is present along with the double or triple bond, it acts as a chromophore. These are few examples: nitro group, carbonyl group, etc. And we have another term known as oxochrome. Oxochrome is a functional group. Itself doesn't have any color, but whenever it is attached to any kind of chromophore, it modifies the ability of a chromophore to absorb light by altering the wavelength and intensity of light. So whenever, see, here we are observing two terms: altering the wavelength or intensity. Altering the wavelength means either it will increase the wavelength or decrease the wavelength. If it increases the wavelength, that is what we have one more topic, that is shifts. If it increases the wavelength, it is towards the higher wavelength, right? So when you go with the visible region, which color comes in the last? That is red. So that is the reason why whenever you see the absorption at the longer wavelengths, it is known as bathochromic shift or red shift. In the same way, if the wavelength decreases, so which color comes nearer to that is blue color, that is violet indigo blue. So it's almost nearer to blue color. That is the reason why it is shorter wavelength. So that is why it is known as hypsochromic shift or blue shift. So whenever this is regarding, whenever it alters the wavelength, the presence of oxochrome will alter the wavelength, means bathochromic and hypsochromic shift is what you will be observing. When it alters the intensity, if the intensity is more, optical density or absorbance is more than what you are expecting. If it is higher, it is known as hyperchromic shift. If it is lower, it is known as hypochromic shift. So these are the different types of shifts you will be observing whenever oxochrome is present along with the chromophore. Let's see one example here. See benzene molecule. Generally, benzene is an aromatic ring which has a lambda max of 255 nanometer. Now, what is lambda max? So whenever we plot a graph taking wavelength on x-axis and absorbance on y-axis. So the wavelength at which you will observe the maximum absorbance, it is known as lambda max. So for the benzene, the lambda max is 255 nanometer. So coming to phenol group, what is the oxochrome that is present in the phenol is OH. Right? Benzene ring with OH is known as phenol. So when you see the lambda max here, you are observing a bathochromic shift because it is 255 nanometer and 270 nanometer here. And the another oxochrome here, if you see aniline benzene ring with amine group, that is NH2. So you're seeing the lambda max at 280 nanometers. So benzene itself has 255 nanometers. Whenever you are having oxochrome with this chromophore, what happened? You have observed bathochromic shift. In the same way, if it decreases, you can say it is a hypsochromic shift. So that is how the terms are related in the. So how you will, these shifts will help us in the structural elucidation of a compound. Then next one is coming to the theory of the UV-visible spectroscopy. As we have seen principle, that is the absorption of UV-visible light will take place whenever there is a molecular transition from the ground state to the excited state. Okay, so here in the UV-visible light, if you see the theory of UV-visible light, whenever a light falls, that is maybe a UV light, because we are talking about it, whenever UV-visible light falls on a solution of a homogeneous media, what happens here? The instant light is always equivalent to the sum of it is reflected, some of it is absorbed, and some of it is transmitted, which is given by the following equation. I naught is equal to IR plus IA plus IT. I naught is the instant radiation, IR is the reflected light, and IA is the absorbed one, and IT is the transmitted one. Since the reflected rays is almost less than 4%, it is normally neglected. So generally we say that the incident light is equivalent to the absorbed light plus transmitted light, and this equation is more explained detailedly with one law that is known as Beer-Lambert's law. So what does Beer-Lambert law state is, so the amount of light absorbed by a substance is directly proportional to the substance concentration and the path length of the light. So what it says, the absorbance A is equivalent to the ECL, that is directly proportional to the concentration, and L is the path length, E is the molar absorptivity. So if you see here, I naught is the instant light, some of it is absorbed and some of it is transmitted. Generally we don't talk about the reflected light. Okay, so how did we get this equation? Let's see a brief outline of the derivation of Beer-Lambert's law. So what does Beer's law say? First thing, so whenever a monochromatic light is passed through a homogeneous absorbing medium, the rate of decrease in the intensity of radiation with the concentration of the absorbing increases with the absorption of the species, and which is directly proportional to the incident light. So here, if you see, minus di by dc is equal to ki. Here minus indicates the decreasing intensity of the radiation, and di by dc is the intensity and the relationship with the concentration. So if you remove this integration and you get it, this natural logarithm I is equal to kc plus b. So by substituting values, assuming that concentration is 0 and I is equal to I naught, we get a b value if we see here, right? minus natural logarithm of I. So we have to substitute this equation in the one and you will be getting this. So finally it proves that I is equal to I naught e to the power of k minus c. So this is what Beer laws say, that intensity is directly proportional to the concentration. So whenever we go to the Lambert's law, it says that the rate of decrease in intensity of the radiation differs with the thickness of the absorbing media is directly proportional to the intensity of the incident light. So in the same way, how we reduce the di by dc is equal to ki, in the same way di by dt is equal to ki. So here dt is difference in the it relates to the thickness. So minus symbol, negative sign indicates about the decrease in the intensity. So when same way by deriving the same formula, we will be getting I is equal to I naught into e to the power of minus kt. This is the Lambert's law. So by combining both Beer and Lambert's law, we get this equation, that is I is equal to I naught e to the power of minus kct. So finally, whatever we seen in the theory, that is A is equal to ECT, is what we have derived here, that this is the mathematical equation for the Beer-Lambert's law. So let's see each one by one. A is absorbance, E is the molecular extinction coefficient, C is the concentration of the sample, and T is the path length. So when you see the equation, here it is directly indicating that absorbance is directly proportional to the concentration and thickness. Thickness is generally, I mean path length. Path length is normally 10 millimeter or 1 centimeter. And this is molecular extinction coefficient. Molecular extinction coefficient is also given by the formula specific absorbance into molecular weight by 10. What is specific absorbance? It is defined as the absorbance of 1% W by V solution present in cell of 1 centimeter path length. So this is all about Beer-Lambert's law. See, if we plot a graph taking concentration on x-axis and absorbance on y-axis, generally in Beer-Lambert's law, if that solution follows Beer-Lambert's law, you see this as an ideal solution. Ideal one, that is, you will find a straight line passing through the origin. But this is not actually happens. Sometimes you will see a concave upwards and sometimes concave downwards. When you see concave upwards, it is known as positive deviation, and whenever you say concave downwards, it is called negative deviations. Positive deviations are something you will observe where there is very minimal change, I mean less change in concentration and more change in absorbance, large change in absorbances. Coming to the negative deviations, you will see large change in concentrations and less change in absorbances. So what are the reasons which will lead to this kind of deviations? Let's see. The first one is real deviations. Generally, Beer-Lambert's law, that will be followed only for the dilute solutions. So if you are using concentrated solutions, then definitely you will be observing this kind of deviations because of the change in the refractive index of the samples. Solution changes, or whenever the concentration increases, obviously the refractive index will change and there will be change there, you will be observing the deviation. And the other one is, like for example, in the chemical deviations, you can say association or complex formation, hydrogen bonding, or presence of impurities. These all comes under chemical deviations, which will lead to chemical deviations. Then coming to the instrumental deviations, see, we have seen in the definitions itself, whether it is a Beer's law or Lambert's law, we are just talking about the monochromatic light. So whenever polychromatic light is used, then obviously there will be a little bit of deviation. Then coming to fluctuations and then sensitivity of detectors. So there are various reasons which are causing the deviations in the Beer-Lambert's law. So this is what, even though in spite of having these deviations also, because we are following, we will be using solutions for analyzing. Generally in UV, solutions are used, liquids are used for sample analysis. So we expect that all the samples will follow this Beer-Lambert's law, because of which we can plot a calibration curve and then you will be able to get the unknown concentration. So believing all the sample solutions which we are taking follow the Beer-Lambert's law, that is the reason it is very important when you are studying UV-Visible spectroscopy. Then let's see the instrumentation of UV-Visible spectroscopy. Coming to the components of UV-Visible spectrophotometer. The first one is source of radiation. So this is the source of radiation, collimating system, and monochromator system. Generally, collimating system and monochromator system is like an integrated one. It starts with entrance slit, then collimating lens, then monochromator, collimating lens 2, and then finally exit slit. So it is like a combination, right? First you will have a lens, then monochromator, again a lens, and then a slit. So you will understand once when we go in detail about the instrumentation part. Then coming to this lens, grating, wavelength selector, all this comes under collimating system and monochromator system together. Then sample holder, detector, finally amplifier and readout device. So let's see sources of radiation. The first one is tungsten halogen lamp. When I say tungsten halogen lamp, it is generally our household lamp, whichever we have. It looks like same in that way only. So in between, in the bulb, it is a bulb which is filled with inert gas, and we have a tungsten filament. So it can be heated up to 3000 Kelvin. 3000 Kelvin. Okay. Beyond that, the tungsten gets sublimating. So and it is also used when polychromatic light is used. Generally you will be using and the demerit of tungsten halogen lamp is the major portion of the energy whichever it is giving, it will be giving near IR region. Because we are using in UV visible, this is considered as a demerit. So it can be used whenever IR spectroscopy. Then coming to the hydrogen discharge lamp. In the hydrogen discharge lamp, we have a pair of electrodes in a glass tube, which that glass tube is filled with hydrogen gas. And it also has one small window, like silica or quartz window for letting the UV radiation to pass into it. Okay. So whenever a current is passed, what happens at a high voltage, the electrons are discharge of electron occurs, and then which will excite the hydrogen molecules, and which will again in turn make it to emit UV radiation near the UV region. Generally, hydrogen discharge lamp or deuterium lamp, these are what which we use for UV sources. Next one is xenon discharge lamp. In the xenon discharge lamp, we have two tungsten electrodes that are separated by some distance. Okay, so these are also enclosed in a glass tube, and we have filled with the xenon gas under pressure. Then what happens whenever a voltage is applied, an intense arc kind of thing will be generated between the two electrodes. This is actually a good source whenever because it's a continuous spectra. Our UV visible spectroscopy is a continuous lines you will be getting. When you see a UV visible spectra, you will be having continuous spectra, right? You will not be observing like discontinuous thing like in mass or something. You will be seeing different kind of lines you will not be seeing, right? The spectra is continuous. So that is the why this xenon discharge lamp will help us to, it gives good radiation, and continuous source of energy is available with high intensity. One disadvantage or demerit of this xenon discharge lamp is because of it operates at high voltage, the during operation it becomes very hot. So whenever you're using a xenon discharge lamp, you should have a thermal insulator along with it. Then the last one is the mercury arc lamp. In the mercury arc lamp, what we see is the mercury vapor is stored under the pressure, and the excitation of atoms is done by the electric discharge, because it doesn't give continuous radiations, because of which we will not be using it in the UV visible. We will not use more in the UV visible spectroscopy. So the most widely used sources, hydrogen discharge, deuterium lamps, like that we will be using for the UV radiation as a source of UV radiation, UV visible radiation. Then next is the collimating system. As I've already mentioned before, collimating and monochromator system comes together hand in hand. So in the collimating system, what happens is whatever radiations that comes under, in whichever direction they come, we try to make it parallel so that it will get into the entrance slit. So actually our collimating system start with the entrance slit and end with the exit slit. So we are having different types of collimating systems. For example, if you see here, we are seeing about lenses, mirrors, and slit. What are lenses? Lenses is something just like which we wear for spectacles, right? Specs, we will be having lenses the same way. Those kind of lenses only we'll be using. They are actually transparent, and then they are suitable for UV. We have different types of materials the lenses are made up of, right? So ordinary silicate glass, whichever we are using, it can be used in UV region because it can transmit up to 350 to 3000 nanometers. Whenever you are using less than 300 nanometers, then the lenses material like quartz or fused silica is used. This is one of the collimating system, and the next one is mirrors. In the mirrors, if we see here, they are used to reflect, focus, and collimate the light beams into the spectrophotometer. The whatever mirrors we are taking from the front surfaces, they are aluminized. Okay, so why do we do that? Because to minimize the light loss, whatever light is falling on the mirror, completely it is getting transmitted. So that is the reason why we do the aluminization to the front surface of the mirror. Then coming to the next one is slit. So generally, if you see any UV visible spectrophotometer, these are the what you will be seeing in the collimating system. That is lenses and as well as slits. You have to, why we use this slit is it is a very important device for resolving the polychromatic radiation into the monochromatic radiation. Okay, so whatever all the radiations are coming, we can't use all that, right? Only we have a desired wavelength that is only called as lambda max. So that is the reason why we have to use these slits where the polychromatic, for resolving the polychromatic light into the monochromatic light radiation. Okay, so I have already told you, for this reason, we are having two slits. Entrance slit will take all the polychromatic light, and exit slit, it will send only the monochromatic light. So which plays a very, and the slit width also plays an important role. If this, we have seen the deviations from the Beer-Lambert's law, right? Slit width also plays an important role for the resolution of polychromatic radiation. So this is about the collimating system. Next comes the monochromators. In the monochromators, we have seen, so from in the monochromators, what happens? From the radiation, from the isolated radiation, what is the desired wavelength that should be selected? That is done by this monochromator. Okay, so the essential elements of monochromator are entrance slit, dispersing element, and exit slit. So here we have seen in the entrance slit what happens. It defines the incoming heterochromatic radiation, and dispersing element will disperse the heterochromatic radiation into its component wavelength, and exit slit will send whatever it has selected, whatever wave, with the help of wavelength selector, whichever wavelength has been selected, that will be coming out of the exit slit. So we will see about this dispersing elements, what are the different types. So following types of the monochromatic devices are used. They are filters, prisms, and gratings. Depending upon the instrument, these devices are incorporated into the instrument. So coming to the filters. In the filters, we are having two types of filters: absorption filters and interference filters. When I say absorption filters, what it works by selective absorption of unwanted radiation. Whatever unwanted radiations are there, it will absorb, and it will transmit the radiation which is required. It's very good. So this is very easy kind of thing which you can incorporate, and less expense instrument which are available will be using filters as a monochromatic for segregating the polychromatic into the monochromatic light, and for selecting the wavelength, desired wavelength. Then an absorption glass filter is made up of solid sheet of glass that has been colored by pigments, which is dissolved or dispersed in glass. So examples of this is glass and gelatin filters. Next are the interference filters. So interference filters are something like you're doing a online shopping app. So whenever you want a specific thing, when you want to buy a specific thing, you will be filtering all the things, right? Whatever you don't want, whatever you want, you will be selecting. So what happens to the remaining will get automatically rejected according to your criteria which you have selected. In the same way, here also in the interference filters, what happens is, whichever unwanted wavelength is there, no, that will be gone out in like this in selective reflection. The only one which is required, or the monochromatic light which is having the desirable wavelength, only that light beam will be sent out of the exit slit, so that it will go and fall on the sample solution. So this is how it takes place. So coming to the band pass, see, band pass is something which says about like this much amount of nanometer difference will be seen. For example, if I say in the absorbance filter, you have 30 nanometer. So up to 30 nanometer band with the band pass is like very high compared to the interference filter. So in the interference filter, if you see here, how it is made up of is, it is constructed by a two parallel glass, if you see here, and which has inner inner side of the glass plates is having a silver lining, and between those two plates you will be having one dielectric material like calcium fluoride, silicon dioxide, like that you will be having with different refractive indexes. So that is what will help us in what you call rejecting the unwanted wavelength. Okay, so coming to the band pass, because of its narrower band pass and higher transmittance rate, interference filters are mostly chosen compared to the absorbance filters. Then coming to the next one, that is prisms. In the prisms, generally they are made up of glass, quartz, or fused silica. So whenever we say in anything which we use in UV visible, it should be transparent. So whichever materials are transparent, all those kind of materials you can take and use for even it can be a prism or an absorbance filter or next coming gratings or cuvettes. These are the materials which you will be using for construction of that particular component. Okay, so prism is made from glass, quartz, or fused silica. So the quartz or fused silica is generally a choice of material for UV spectrum. Now what happens here is, if you see this prism, this is refractive prism. In the prism also we have two types of prisms, refractive and reflective. Coming to the refractive prism, this is how it acts. Here the white light will pass through the prism, and now when it goes into the prism and comes out of the prism, the dispersion of the polychromatic light occurs, and from this, with the help of wavelength selector, whichever wavelength we need, that will be coming out of the exit slit and then falling on the sample solution. Okay, so this is the mechanism of action for the refractive prism. So this is the mechanism for the refractive prism. Then coming to the reflective prism. What happened to reflective prism is, so one side is aluminized. Okay, so one side aluminized. Then what happens? The rays which are incident from the same side, the reflection also will take place. So white light will fall and the reflection will take place. The reflection is nothing but dispersion of the light in the same way. If you see in the refractive here, it is in opposite side. Incident beam is on one side and refraction is on the other side. Coming to the reflective, incident reflect means same side. Incident and reflection will take place in the same side. So by rotating the prism or by changing the exit slit, the wavelength will be selected when we use prisms. So this is the mechanism behind the selection of wavelength in while you are using this as monochromators. Then prisms as monochromators. Then coming to the gratings. So in the gratings, these are the most efficient things which are helping us in converting a polychromatic into a monochromatic light, and it has a resolution of plus or minus 0.1 nanometer. They are, whenever spectrophotometers whatever we are using which are expensive, the gratings are the thing which we use. We have two different types of gratings, that is diffraction grating and transmission gratings. So in the diffraction grating, if you see here, the mechanism of this is reinforcement. Reinforcement means strengthening of the radiation. So what happens? See, here in the diffraction grating, the incident light is reinforced compared to that of the diffracted light. So what happens? This is more strong, because of which it doesn't get reflected. Okay, it gets diffracted. Coming to the transmission gratings, this is like I have told about reflective prisms, right? The same thing you can see here in the diffraction grating. Coming to the transmission gratings, here if you see, this is the incident light, and here the refracted, whatever refraction you are seeing here, that is reinforced here. Refractive light is reinforced here. So that is the difference between the diffraction grating and transmission grating. However, it is, we can see 100% transmittance of the radiations whichever are coming into whatever incident light is falling on the gratings. 100% transmission is the one which is kept in mind for gratings, as we have seen the resolution here, right? 0.1 nanometer. So almost all the wavelength, whatever wavelengths that has been coming or falling, the light, instant light is having, almost all will be coming back and fall on the sample. That is what we are trying to say here. That is why gratings are most widely used. Whenever you see any diagram like single beam, double beam, when you check out, you will find gratings as the monochromator devices, like for conversion of polychromatic into monochromatic light. So we have seen all these three different types of monochromators, right? Filters, prisms, and gratings. Then coming to the sample holder or cuvette. Whenever I say sample holders, again, generally for holding the samples, liquid samples, we will be using cells or cuvettes. They are rectangular or cylindrical in shape. As I've already mentioned, UV visible, we have three materials. So whenever you are using for the UV region, it is prepared for quartz or fused silica, and whenever you are using in the visible region, fused glass is used. Okay, so whenever we are handling the uh, samples, whenever we are handling the liquid samples, we see that uh, the surfaces of the absorption cells must be clean, and then there should be no fingerprints. Then cleaning is carried out while washing with the distilled water, or with what the cuvette should be cleaned with the distilled water or dilute alcohol and acetone. Then it should fulfill three conditions. That is, it should not react. Materials of construction should be inert to the solvents, and it must transmit all the wavelength whichever we are using, and the construction should be uniform, thickness must be constant, and the surface which is exposing to the light should be optically flat. So when it satisfies all these conditions, then it can be used as a sample holder in UV visible spectroscopy. Then next